Hello everyone. Today let's solve the problem number 191, number of 1 bits. So what the question states here, we are given a positive integer n here. You can clearly see here. So we are given a positive integer n and we need to count the number of set bits or ones in its binary representations. So we have to convert this one to the binary and we have to check how many number of set bits 1 is present in its binary representation, right? We have to count the number of set bits once in its binary representation. This is also called as Hamming weight, also known as Hamming weight, right? So that's what the question states here. In this case, see, the input binary string 1011 has total 3 set bits, means 1, 2, 3 here. You can clearly see. So same goes with the example 2 and example 3 as well. So 1 to 8 we have here. This one 1 to 8 is represented in the binary format like this, in this way. So here we have 1, so we have to return that 1. So we have 3 ones here. In this case we are returning 3. We have this much number of ones here in this case. So we have 30. We have to return 30, right? There are 30 months here, so we are returning 30 in this case, right? So I hope this is completely clear. So let me do one thing. Let's discuss the approach first. I hope the question is completely clear. Let's discuss the approach first, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. So initially, what we'll do, let's discuss the approach first. So here, let's discuss the approach step by step, right? So the first thing is, we'll be going with the bit manipulation. So here, we'll be going with the bit manipulation approach. So just keep this in mind. Just give me a second here. Yeah, just keep this in mind. So here, I have considered the same example, the first example that they have given in the question, so that it will be easier to understand the approach, right? So we'll be going with the bit manipulation or Brian Kernighan's algorithm, right? So just keep this in mind. Let's discuss the approach step by step, right? So first thing here is, we will be making use of bit manipulation to count the number of ones in the binary representations of n. That's what we need to do, right? That's what the question is asking here. So first here is n equals 11. We know this. Binary representation of 11 here is 1011. So n equals 1011. So here in this case, last bit is 1. You can clearly see here. So let me write another one here, this one, so that don't get confused here. So the last bit here is 1. So we will increase the count. Nothing but count equals 1. So now right shift is 101. So here now right shift we got here as 101 in this case, right? So just give me a second here. Yeah, it has to be 101. So the next step here is n equals 101 we got. The last bit is again 1 here. You can clearly see here. So let me do one thing. Yeah, the last bit is again 1. So increase the count. Count equals 2 now. Count equals 1 we had in the previous step. Now count we got as 2. So now again shift right, n equals 10. So we will be making use of the shift right. So now n equals 10. Right, n equals 10. Last bit is 0 this time instead of 1. So we should not increase in count. So now let's shift right. Now we have only n equals 1 in this case. So n equals 1 we have, again the last bit is 1 itself. So now we have to again increase the count. Count equals 3. From 2 to count 3. Here we are not increasing in this step. In this step count became 2. In this step count is 3. Right? Now we will shift right. So n equals 0 in this case. So now n equals 0 in this case. N equals 0, loop ends here. Final count is 3 here. So n equals 0. So loop ends. The final count we got here is 3. You can clearly see here. So this we will return as output. This we will be returning as output. So we got the answer 3 here. And the output they have mentioned for the question, for the first example, is also 3. So this is equivalent to the output that we got, or the answer that we got. So the approach works absolutely correct in this case. So this is the approach that we will be going with. So Brian Kernighan's algorithm or this one, bit manipulation, right? So I hope the approach is completely clear. So next, let's discuss the edge cases one by one quickly, right? So first thing is smallest input here. N equals only 1 we have, binary representation is 1 and the set bit is 1 here in this case. This edge case just keep in mind. The second edge case here is power of 2. N equals 8 we have, binary 1 0 0 here. In this case set bit is 1. We have only 1 here. You can clearly see here, right? Here this one. So this is fine. The third edge case here is large input. N equals this one they have already mentioned in the question. Same thing. Set bits will be 30. So this one binary representation I haven't written. They have already given the same thing in the example. You can just check it out. Right? 30. So in this case, these are the three edge cases that we have to keep in mind. Smallest input, power of 2, and this one large input, right? So these three edge cases, large input, the code has to work absolutely fine for the large input. So that we have to keep in mind, right? These are the edge cases we need to keep in mind. I hope the approach that we discussed and the edge cases, all the edge cases are completely clear. Now let's start writing the code. Let's start writing the code. Initially, we have to initialize the count of set bits. We have already discussed this one, right? So I'll just go with let count equals 0. So the next step here is we have to loop until n becomes 0. So I'll just put a while loop here, while of n. In this case, we will check if the last bit is 1 and we will add to count. So this one will be count equals count plus n ampersand 1. So here what we are doing, we are checking if the last bit is 1 and we are adding that to the count. So we saw this one step by step, right? If the last bit is 1, then we were incrementing the count. If the last bit was not 1, if the last bit was 0, binary representation, 1s and 0s will be having. So zeros, if the last bit was 0, we were not incrementing the count. If only the count, we were incrementing the count only when if the last bit was 1. So that's what we are articulating that one in the form of code here. That's it. We are checking if the last bit is 1 and we are adding it to the count. So the next step, if you remember, we were making use of the right shift n by 1. Nothing but we were that shifts out last bit. Means we were removing last digit 1 by 1, right? So we were making use of the unsigned. This one right shift n by 1, right? So to remove the last digit. So here we'll be making use of unsigned right shift, nothing but n by 1. So I'll just write in this case like this 1. This is fine. So the final step here is let's return count here. This is fine. So let me format the code once and let me hit the run button. I hope this works. Yeah, you can clearly see here the sample test cases are getting passed here. Means the code works absolutely correct. Let's check whether it works for all the test cases or not. Let me hit the submit button. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct in this case. Let's quickly discuss the complexities for the code that we have written. Right. So here the time complexity, I mean the approach that we went with here is this one, bit manipulation, right? Or Brand-Kamigan's algorithm, right? So we have already discussed this one. The overall time complexity would be, in this case, it would be big O of logarithmic n. Instead of big O of n, it is big O of logarithmic n. Because we are going with the right shift as well as, you can just say we are just going with the bit manipulation mainly, right? Here. So in this case, the overall time complexity would be big O of logarithmic n. Nothing but a number of bits in n, right? So what would be the space complexity here? The space complexity would be here big O of 1. We are making use of few variables. Here we are making use of only a few variables that requires constant space. We are not making use of any extra space here, right? So the overall space complexity would be big O of 1 here. The time complexity would be big O of n and the space complexity would be big O of 1 in this case, right? So I hope this is clear, and I hope the solution or the code that we have written is completely clear as well. For now, this is it. Thanks for watching, guys.